Well, here we go with the final video for Chapter 8, Angular Momentum. We want to be able to, at the end of this video, to compare and contrast angular momentum and linear momentum. We want to be able to calculate the angular momentum of rotating objects and understand the law of conservation of angular momentum. So let's jump right into it. Things that rotate, whether it's a space station or some kind of cylinder rolling down a ramp or a ride at the fair or whatever, things that rotate remain rotating until something stops them from rotating. A rotating object then has what's called inertia of rotation. Now remember, when we talked about momentum, we said that all objects have inertia of motion, or what we call momentum. And momentum is simply the product of mass times velocity. That kind of momentum is linear momentum, momentum of an object moving in a straight line. Similarly, inertia of rotation then will give an object what's called angular momentum, or the momentum of a rotating object. Everything from a planet orbiting the sun to a rock whirling around at the end of a string, and even the tiny electrons whirling around atomic nuclei all have angular momentum. Angular momentum is defined as the product of rotational inertia and rotational velocity. We symbolize angular momentum with an L. This I is rotational inertia, and the omega is rotational speed. So to put all this together, right, angular momentum tells us that anything that rotates will keep on rotating until something stops it. This is referred to as an object's inertia of motion, and that inertia of motion is more commonly called angular momentum. Now, for the case of an object that's small compared with the radial distance to its axis of rotation, such as a tin can swinging from a long string or a planet orbiting in a circle around the sun, the angular momentum can be expressed as the magnitude of its linear momentum, mv, multiplied by the radial distance, r. So that equation can be angular momentum is equal to mvr. Now, just as an external net force is required to change the linear momentum of an object, an external net torque is required to change the angular momentum of an object. So we can state a rotational version of Newton's first law, the law of inertia, to say an object or system of objects will maintain its angular momentum unless acted upon by a net external torque. Our solar system has an angular momentum contributed by the sun, the spinning and orbiting of planets and the myriad other smaller bodies. The angular momentum of the solar system today will be its angular momentum in the future. Only an external torque from outside the solar system can change it. In the absence of such a torque, we say that the angular momentum of the solar system is conserved. And that can be applied to smaller systems as well. And now what we're going to find, we're going to take a look now at the conservation of angular momentum. Just as the linear momentum of any system is conserved if there's no net force acting on a system, the angular momentum is conserved if no net torque acts. So the law of conservation of angular momentum says if no external net torque acts on a rotating system, the angular momentum of that system remains constant. This means that with no external torque, the product of rotational inertia and rotational velocity at one time will be the same as at any other time. An interesting example of the conservation of angular momentum is with this spinning skater. In this first picture here, her rotational inertia is relatively large in this position with arms extended. Now, as she slowly turns, her angular momentum is the product of the rotational inertia and rotational velocity. Now, when she pulls her arms inward, the rotational inertia of her body is considerably reduced, and the result is her rotational speed increases. You can try this yourself if you have a spinning chair or something. Get spinning around with your arms extended and then pull them in, and you'll feel yourself begin to move faster. It's just straightforward physics. This procedure is used by a figure skater who starts to whirl with her arms and perhaps maybe a leg extended, and then draws the arms and leg in to obtain a greater rotational speed. Now, whenever a rotating body contracts, then its rotational speed increases. If a cat is held upside down and then dropped, it's able to execute a twist and to land upright on its feet, even if it has no initial angular momentum. Zero angular momentum twists and turns are performed by turning one part of the cat's body against the other. And while falling, the cat rearranges its limbs and tail several times to change its rotational inertia repeatedly until it lands feet downward. So during this maneuver, the total angular momentum remains zero. When it's over, the cat is not turning. The maneuver rotates the body through an angle, but it does not create continuing rotation. To do so would violate the angular momentum conservation. We can also see the law of conservation of angular momentum in the motions of planets and the shapes of galaxies. It's really fascinating to note that the conservation of angular momentum tells us that the moon is actually getting further away from the Earth. This is because Earth's daily rotation is slowly decreasing due to the friction of ocean waters on the ocean bottom, just as automobiles' wheels are slow down when brakes are applied. This decrease in Earth's angular momentum is accompanied by an equal increase in the angular momentum of the moon and its orbital motion around the Earth, which results in the moon's increasing distance from Earth and decreasing speed. This increase of distance amounts to about 1/4 of a centimeter per rotation. So every time you see a new moon, it's 1/4 of a centimeter further away. Now, this would indicate that in the past, the moon was a whole lot closer to the Earth. Depending on how you count the number of moons that there's been, it could be as huge distance closer. Well, that'll do it for angular momentum and conservation of angular momentum. We'll see you in class.